Hi, everyone. My name is Arjun. I'm a former research intern at Microsoft Research India, and I'm presenting my paper today with Dr. Akshay Nambi and Sumuk Marathe on robust fault tolerance approaches for smoke detectors. Smoke detectors are used widely in network systems, in homes, schools, offices, malls, and more to greatly reduce the number of deaths in fires. Despite this, they still fail to alarm in up to 15% of cases. In the United States, this contributes to almost $10 billion in property damage and 2,000 fire casualties every year. So, coming up with new ways to detect failures to alarm is extremely important for improving safety and reducing lives lost in fires. How do smoke detectors work? We focus on photoelectric smoke detectors, which are the most popular type of smoke detectors. The alternate ionization detectors are being phased out in favor of photoelectric smoke detectors as well. In a photoelectric smoke detector, there's a light source which shows light, and a light sensor, which is typically a phototransistor. In the absence of smoke, very little light goes from the light source into the light sensor. In the presence of smoke, smoke particles will begin to reflect some light from the light source into the phototransistor. Then the phototransistor will detect a small amount of light, and its output will gradually increase. This graph shows the output of the phototransistor over time as smoke accumulates. On the x-axis is time, and smoke begins accumulating at 150 seconds. As you can see, the phototransistor's output, which is on the y-axis, gradually increases over time. Eventually, it reaches a preset alarm threshold, which is the value required for the smoke detector to detect a fire, at which point the smoke detector will trigger an alarm. Why do smoke detectors fail? There's many possible causes of failure. One of them is power failure, which can result from either a battery dying or power to the building being lost. And another example is improper placement, which prevents smoke from flowing to the smoke detector. For both of these problems, significant progress has already been made. In the case of power failure, battery-powered smoke detectors announce when the battery is low, and wired smoke detectors typically come with a battery backup. For improper placement, government standards dictate where the smoke detector must be placed in the building. A major unsolved cause of failure is degradation of the sensing components themselves. So in the case of the light source or LED, many emerging solutions are directed at detecting when the light source is degrading, but much less attention has been paid to the phototransistor. So we focus on the phototransistor, which again is this component which detects the presence of light reflected by smoke. To illustrate how this affects the operation of the smoke detector, we return to the same graph, which shows the phototransistor output as it is exposed to increasing amounts of smoke. The blue line shows a working phototransistor. This orange line shows a faulty phototransistor. So this is a type of fault called drift, where the phototransistor's sensitivity to smoke or sensitivity to light is decreased. So it still responds to increasing densities of smoke. So as you can see, the orange line still increases as the amount of smoke increases, but it increases much more slowly. At a given amount of smoke, the output is lower compared to a working phototransistor. And it takes more time and higher densities of smoke before this faulty drifted phototransistor actually triggers an alarm. This is dangerous because it leaves residents with less time to evacuate out of a building after the alarm is triggered, because the alarm is triggered late relative to a working phototransistor. Another possible type of fault can result from various types of electrical failures. And in this case, the phototransistor output, again, given by the orange line, does not increase at all in the presence of higher smoke densities. To look at this drift in the real world, we conduct some experiments with 12 smoke detectors used in a commercial building for between 1 and 5 years. This graph shows how the phototransistor's sensitivity to light changes. The x-axis is the intensity of light shown into the phototransistor, and the y-axis is the phototransistor output. So for all the phototransistors, as you increase the light intensity, the output of the phototransistor increases, which is standard. The blue line is a fully functional, working, brand new phototransistor, and the remaining lines are ones that had been in use for 1 to 5 years. So as you can see, compared to this blue line, these used phototransistors or drifted phototransistors have a lower response to the same light intensity. So at a fixed light intensity, their output is lower, which indicates that they're less sensitive to light. So to quantify the impact of this on the behavior of an actual smoke detector, we conducted some tests where we exposed the smoke detectors to real smoke. In this graph, the x-axis shows the drift score of the phototransistor, which is a way of quantifying the their sensitivity to light. The left y-axis, which corresponds to the blue bars, indicates the smoke density at which the smoke detector triggered an alarm. And the y-axis, the right y-axis shows, which corresponds to the orange bar, indicates the time at which the smoke detector triggered an alarm. So as you can see in the rightmost set of bars, which are the most drifted phototransistors, it takes more time and higher smoke densities for the smoke detector to alarm compared to the smoke detectors on the left, which are not drifted or which have the least amount of drift. This shows that phototransistor degradation or drift reduces the sensitivity to smoke, and this causes the smoke detector to take more time and higher densities of smoke before it triggers an alarm, which is dangerous and can threaten lives. Now, the key challenge is that a faulty phototransistor can look like a working phototransistor when there's no smoke. What that means is at low light intensities, which correspond to the absence of smoke, all the outputs of the phototransistors are bunched together. They're very close together. And a fully functional phototransistor gives a similar output as a drifted phototransistor. It's only at higher light intensities, which correspond to the presence of smoke, that they actually begin to diverge. So this is a tricky challenge that we have to solve. The industry standard approach is used in commercial smoke detectors, and it's widely used in most commercial models. So what this approach does is it measures the output in the absence of smoke. So when there's low light intensity, it measures the phototransistor's output, and it compares that against a pre-measured baseline. The key assumption is that the output in the absence of smoke gives us an accurate picture of how the smoke detector will actually behave when there's a fire. The idea is, well, we can just measure this no smoke output and use that to tell us, is this a working phototransistor when a fire actually comes? And as we've demonstrated, this is not a good assumption. So the output in the absence of smoke does not, in fact, predict the output in the presence of smoke. So even if a phototransistor gives a similar output as a working phototransistor when there's no smoke, it may not give a similar output when smoke actually appears. So the industry standard approach can give us false negatives, i.e. indicating that a phototransistor is working when it's really not. To illustrate this, this graph shows the relationship between the output of a phototransistor in low light on the x-axis versus in high light on the y-axis. So each point corresponds to the output of one single phototransistor. And the assumption of the industry standard approach is that you can use the values on the x-axis in order to predict the values on the y-axis, i.e. you should be able to tell just from the output absent smoke or in low light in order to figure out how it'll behave in the presence of smoke or in high light. As this graph shows, there's very poor fit between these two things. The correlation is very poor. So the industry standard approach cannot accurately use the low light phototransistor output in order to infer how the phototransistor will behave in the presence of light, in the presence of smoke. So the key challenge then is, how can we determine if a phototransistor is working, drifted, or faulty without actually seeing smoke? And we propose two solutions. The first is FallTime, which is a way to test fundamental device properties. And the second is a mechanical test button, which simulates the behavior of smoke. In both cases, we know in advance what a working phototransistor behaves like, and we compare this against the behavior of a phototransistor deployed in the field to determine if it's working, faulted, or drifted or faulty. Digging into what the FallTime approach does. So there's an electrical property called capacitance between the phototransistor's base, or the part that absorbs light, and the phototransistor's emitter, which is the part that gives the output. Capacitance stores charge. What that means is when light to the base is turned off, the phototransistor does not immediately see its output fall to zero. Rather, it takes some time because this charge stored in the capacitance has to take time to discharge. So this graph shows the phototransistor's output after light is turned off. On the x-axis is the time after light is turned off, and the y-axis is the phototransistor's output. So rather than immediately falling to zero, it takes time because that capacitance between the base and the emitter has to discharge all of the charge that it is stored. So you see a curve that slowly decreases over time instead of decreasing immediately. Now, drift is caused by an electrical phenomenon called hot carrier injection, in which electrons basically gain enough energy to start causing damage to various parts of the internal phototransistor components. It also happens that this hot carrier injection reduces the base emitter capacitance. So what we see in drifted phototransistors is that the capacitance is lower between the base and the emitter, and that means it takes less time for that capacitance to discharge. So this orange line gives an example of a drifted phototransistor, and as you can see, it discharges faster. So this fall curve is sharper and decreases faster. Fall time refers to the amount of time it takes for the phototransistor to go from this high value down to zero. So in the orange line, the fall time, which is a fundamental key electrical characteristic of phototransistors, is shorter and smaller compared to a working phototransistor. So the more drift there is, the shorter and shorter the fall time gets. So in an even more significantly drifted phototransistor, the fall time is even shorter. The fall time fingerprint has three key properties. So first, it's distinct between working, faulted, and drifty components. This graph shows that two working phototransistors, given by the blue and orange lines, look very similar. They look different compared to the three drifted components, which are the green, red, and purple lines, and they look very obviously different from this faulty component given by the purple line. Second, fall time correlates very well with drift. So the x-axis gives the drift score, which is again a way of just quantifying the phototransistor sensitivity to light, and the y-axis is the fall time. And as you can see, there's a great linear relationship between the two. The purpose of this is to quantify the amount of drift. So if we can model this linear relationship beforehand, then we can simply measure the fall time of a phototransistor and see where it falls on this line, essentially, in order to determine how much drift is in the phototransistor. Finally, fall time is robust to variations in the environment. So even as the temperature changes from 33 to 84 degrees Celsius, the shape of this fall time remains basically the same, and the actual fall time value is the same. And the same goes for the presence of dust. The change in the fall time from dust is very minimal compared to the actual change from drift. Now let's turn to our second proposed solution, which is this mechanical test button. The key idea is, in order to predict the behavior of the smoke detector when smoke arrives, just simulate the presence of smoke. Smoke just reflects light from the LED into the phototransistor, so we design a mechanical test button that protrudes into the sensing chamber when pressed, that also reflects light into the phototransistor like so. The key idea is when you press the button, you just measure the phototransistor output and compare that output against a working phototransistor to come up with how drifted that phototransistor is. And it has the same three key device properties as fall time. Counteracting drift. So in order to, we measure fall time, and all we do is we measure fall time or the test button output in order to come up with how much drift is in a given phototransistor. And the purpose of this is to apply gain to the phototransistor output. So if the phototransistor is drifted, its output is lower. So we can just multiply its output by some factor in order to increase it so that it approximates the behavior of a working phototransistor again. So again, this graph showed how a faulty or drifted phototransistor compares against a working phototransistor. And the key idea is we just amplify the output of a phototransistor from a drifted component in order to get it to work just like a working component. And as mentioned earlier, we just use a linear model to estimate the amount of drift. And from that drift, we can come up with exactly how much gain to apply. To evaluate this approach, we manually degrade the detectors using techniques from highly accelerated lifetime testing and expose the detectors to increasing densities of smoke. So we generate smoke in this left chamber, which is pumped into a right chamber containing the smoke detectors. We test this with 2 commercial detector models and 3 custom detector models. In the commercial detectors, which use the industry standard approach, we find that even with the industry standard approach, they still take a very long time to alarm. So this shows that the industry standard approach does not accurately correct for drift in the phototransistors. In the custom detectors, we apply these three approaches, industry, FallTime, button, in parallel, and compare their behavior against a working smoke detector. So this graph shows an example of a working smoke detector's output. So as smoke increases over time on the x-axis, the phototransistor's output on the y-axis gradually increases as well. Eventually, it crosses this alarm threshold, at which time the smoke detector will indicate that there is a fire. This blue line shows the behavior of a drifted phototransistor. So as you can see, it's still increasing, its output is still increasing as the density of smoke increases, but much more slowly, and it never crosses this alarm threshold. So the key challenge is coming up with a way to quantify how much it's drifted and amplify its output so that it matches the behavior of this working smoke detector. The red line indicates how the industry standard approach performs. It applies a very small amount of gain, and while this means it increases a little bit more compared to the raw unamplified output, the increase is very minimal, and it still never crosses this alarm threshold. In contrast, the FallTime and button approaches apply much more gain, and the result is that the behavior of this smoke detector works just like a working smoke detector. So it increases at almost the same speed, and it crosses this alarm threshold at almost the same time as well. So this shows that our approach better approximates the behavior of a working smoke detector compared to the industry standard approach. To extend these results a little bit, we repeat this type of experiment 20 times and measure the time and the smoke density when each smoke detector alarms. And we find that the button and FallTime approaches alarm 40% faster than the industry standard approach, which represents a great improvement in terms of fire safety. In conclusion, in real-world experiments, we show that phototransistor drift is widespread and reduces the speed of a smoke detector in responding to fire. We present the FallTime fingerprint, which measures drift using electrical properties, as well as a mechanical test button to simulate the behavior of smoke to measure drift. We conduct tests with real smoke to assess these approaches, which show that our approaches outperform existing solutions and can greatly improve fire safety. Thank you everyone for listening, and I'd love to take some of your questions.